In this video, I'm going to show you how to change the clock speed of the microcontroller from 8 MHz to 48 MHz. This is an STM32F030 microcontroller. The STM microcontrollers have an internal clock and an external clock, and each of these clocks have a low speed and a high speed. The high speed internal clock is the HSI, and the low speed internal clock is the LSI. The external ones, which we'll talk about in another video, is the HSE, which is high speed external, and LSE, which is low speed external. In this particular microcontroller, the default speed is 8 MHz, 8 million cycles per second. Inside the ARM microcontroller, there is a pulse, very similar to like a heartbeat. But the pulse of a microcontroller looks more like this. And within each pulse, an instruction is able to be carried out, very similar to the instructions or like the code that we create, but these are more low-level instructions. But you don't really need to know that. But in some circumstances, you need this pulse to be faster. At default, this particular microcontroller, this is the STM32F030, it runs at 8 MHz. And that is using the internal oscillator. It's a RC resistor capacitor oscillator, which is not really that important, but you do need to know that this is the HSI, the high speed internal oscillator. And this microcontroller has the ability to run at 8 MHz using this internal oscillator, or it can run at higher speeds using the PLL clock. So this is the internal oscillator, which is already available to you. The speed of this internal oscillator can be varied. You can pre-scale this, or you can divide this into a smaller speed, like maybe 4 MHz if you wanted to divide it by 2, or you can increase this speed using the PLL, which is a multiplier. And all you need to know is that this PLL allows the internal clock, the HSI, the high-speed internal clock, to be multiplied. But it's multiplied by this speed divided by 2, which is 4 MHz. So let's go ahead and try this out and see what we can do with this internal HSI, high-speed internal clock, and how we can make the clock speed faster using the PLL. The circuit you're going to need is the microcontroller that is on a breakout board, and the breakout board is connected to 3 breadboards. There are multiple power pins that need to be connected. The power pins are 64 and 63. Pin number 64 is connected to the positive, which is positive 3.3 volts. And the pin number 63 is connected to ground, or the negative. I've connected an LED to pin number 37, but you don't need to do this for this particular project. I'm tying the breadboard power rails together using these wires here. Pins number 31 and 32 are also power pins, and pin number 32 is connected to the positive, and pin number 31 is connected to the negative. Pin number 1 is also a power pin, and it's connected to the positive. Because the PLL clock uses the VSS-A and VDD-A to power its clock, pins number 12 and 13 need to be connected to the power as well. Pin number 12 is connected to the negative, and pin number 13 is connected to the positive. So let's create a new project and see what we need to do to change the system clock on the microcontroller. I'm going to use the STM32 CubeIDE, and I'm going to start a new project. You can use this icon here, or you can go to File, New, and I'm going to select STM32 project. Let me go ahead and select the microcontroller that we're using. And in my case, I'm using the STM32F030R8. So I'm just going to press the Next and name this Change System Clock Speed, and I'll press Finish. Okay, so there are a couple ways you can change the system clock speed, and that is using the clock configuration and the pinout and configuration. So you can take a look here and go to the RCC, and there are some parameters you can change. I'm not going to be doing any changes in here, but when I get into doing the high-speed external clocks, I will go into this. So I'm going to go straight into the clock configuration, and this is actually a pretty simple graphic representation or a block diagram of the system clock in the STM32. and it shows you the low speed external, high speed external, and these are the two external sources that you're able to use. The low speed external can accept up to 1000 kilohertz, and the high speed external can go up to 32 megahertz. But that's only at the input of the microcontroller. You can actually change its speed after the input. So you could essentially multiply that speed using the PLL multiplier. In this case, we're going to be using the HSI, which is the high-speed internal oscillator. And you can see that the HSI right now is at 8 megahertz. That's default. And if you wanted to change the low speed, that is at 40 kilohertz at default. So if you look at this block diagram, if you follow the traces with the HSI, you'll see that it goes to this little control here. And it gives you the ability to control what you're going to be using as the main clock. Are you going to use the HSI and then you're going to maintain the 8 megahertz? Or are you going to change it to the PLL CLK, which can also change it? You can see that I have a problem here and it tells me where I have the problem. I can click on resolve clock issues, or I can just pick the down arrow and change the value. And you can see that when I change the multiplier and I have this selected, you'll see the output is 16 megahertz. But I'm multiplying this by 4. Shouldn't I be getting a 32 megahertz? But if you trace the lines over here, the HSI, if you trace all the way down, you'll see that it's divided by 2 here. And then it goes into the PLL multiplier. So first, your 8 megahertz is divided by 2, which is 4. And then it multiplies by 4, which is 16. And then it goes on from there. You can change prescalers, dividing the clock further if you want to. You can divide the clock over here, which goes back down to 8. You can divide it over here. You can change some of these features or peripherals to different speeds. We're going to maintain a non-division. But in our case, we want to change it to 48. So we want to multiply it by 12. So when we multiply it by 12, you'll see that it shows the value as 48 megahertz. And you can also see that it's changed here as well. And you have the option of changing it here. Let's say we want to change this to 24. What will it do? Okay, so 24. By changing this to 24, I'm essentially changing it to 24 over here. And what it did is it automatically changed this to 6. So we want to go back to 12, and you'll see that it goes back to 48. And I can change this back down to dividing by 1, so it doesn't slow this one down. So it takes a little bit of getting used to looking at this block diagram, but it's pretty simple after you look at the tracing of where these things go. If I go back to the HSI, you'll see that it goes back to 8. If I wanted to change this manually to 48 and press enter, it says no solution, but you'll see that after I accepted that, it changed this to 12. It changed this PLL CLK to be operating under the PLL clock. It accepted that value. So let's go ahead and save, because you'll see this little asterisk here. It's telling us that this file hasn't been saved. And once we save it, it will want to auto-generate the code for us. So this is sort of the easy way of creating the code to change the system clock. But I'll also show you a manual approach as well. So let's go ahead and save it. You can also click on this button right here, Device Configuration Tool, Code Generation. And if I press this, it'll also generate the code. I'm just going to go ahead and save it. And it'll ask you, do you want to generate code? And I'm going to say yes. And I do want to open the main.c file. And here is the code that has all of the commented code telling you where you can place your code. I don't generally look at that. It does create a lot of bloat in your code, but just ignore it at the moment, because I may want to change the values in the IOC file. And if I take all of the comments out, it will put the comments right back in once it generates the code again. So I'm just going to keep these comments in here. All right, this is the portion of the code that was changed automatically. You can see that it's using the HSI in the beginning, the oscillator type. The HSI is on because it has to use the HSI and the PLL to operate. The PLL is just multiplying the high-speed internal oscillator. And you'll also notice that the PLL is on. The PLL source is the HSI. It wants to use the HSI and not the external. It's using the internal. If we were using the external, it would be using the PLL source of HSE instead. It's multiplying it by 12, and you'll get a resulting 48 megahertz. And in this condition, it's making sure that this process is completed. And in this section of code, it is changing the clock source to the PLL-CLK. And with the AHB and the APB, which we'll go through later in other videos, it is not dividing it by anything except for 1. You can see that here. The AHB prescaler is divided by 1, and the APB prescaler is divided by 1. But that's not really that important in this particular video, so you don't have to really worry about that. I'm going to go back to the main.c, and once we program the microcontroller with this code, the microcontroller will be running at 48 megahertz. But how do we really know that? And I'm going to test this using a variable. So I'm going to add a variable outside of the main, so it's a global variable. I'm going to put it inside this user code begin 0. And I'm going to use a variable called test counter. It will be a volatile variable. And there's no real explanation on why I'm using the volatile, except that it will keep this active during the operation of the microcontroller. You need to use the volatile keyword to make sure it's not optimized out. And it's going to be an integer. And the name of this variable is going to be called test count. And I'm going to assign it as 0 at the beginning. And I'm going to use the counter to determine whether this microcontroller is actually running at 48 megahertz. To verify that the microcontroller is actually running at 48 megahertz, I'm going to use the timer. And the timer works like this. The timer will use the internal clock, and I'm going to use timer 1. And this is how we'll be writing it in code, timer 1. And the timer 1 will be running at 48 megahertz, unless we prescale it or divide it down. I want this variable that we just created to tell me when 1 second has elapsed. So since the timer 1 is at 48 megahertz, I'm going to use the prescaler, which is a way to divide this down to a smaller number. So instead of the timer counting up to 48 million cycles per second, I want it to count up to, let's say, 1,000 cycles per second. So to do that, we would divide it by 48,000. This is the prescaler. So now the timer is counting at 1,000 times per second. So what I want to do is I want to make sure that there is a trigger in the timer that will tell me that it's reached 1,000. So we're going to create a sawtooth pattern here. So the timer is going to be going up, and instead of it keep going up and then just counting indefinitely, we're going to use the ARR, which is this top level here. And the ARR is going to be 1,000. So when it's reached 1,000, it will drop back down to 0. And then it will count up again until it reaches 1,000. And then it will drop back down to 0. It'll count up again to 1,000. So at each 1,000, because we divided it by 48,000 at 48 megahertz, the timer 1 is counting at 1,000 pulses per second. So if we have a top value of 1,000, then we should get this trigger every second. So let's go ahead and try that out. I'm going to enable timer number 1. Timer number 1 is in the reset and clock control register under the advanced peripheral bus enable register. And we're going to we're going to set the bit for the timer 1 enable. So let's take a look at the registers for the timer. So this is the timer number 1. It starts at page 220. You can read the chapter if you want, but I'm going to go straight to the timer control registers, which is the 267. And you can see that there is, the first one is time 1 CR1. But before we do that, we need to enable the timer in the advanced peripheral bus. So if you take a look on page 113, you'll see the description of the advanced peripheral clock enable register, RCC APB2ENR. This is what we put in our program. Inside of this APB2ENR register, you'll notice that timer 1 enable bit is located here. You need to turn this bit on or set this to 1 for this register. So let's go ahead and do that. We're using the OR bitwise operation to set the bit. I'm going to use the control space to look at all of the things that I can change. And the timer 1 is located right here. Okay. And I got a comment stating that the video that I'm showing how to set and how to reset bits, like using this OR bitwise operation and the AND not bitwise operation, is a bit of a misnomer because this is actually a mask. It's not really setting a particular bit number. And that is true, but there really isn't any need to understand bitwise operations and truth tables at this point. Just knowing how to set and reset bits is perfectly sufficient at this point. If you want to learn more, I'm going to put a card at this position of this video, and you can watch my old video in the AVR series on how to do bitwise arithmetic using the AND and the OR, and how to use masks, which is what this really is. If you look at it, you can see that it's taking a single bit, which is a 1. It's actually 1 in decimal and 1 in hexadecimal as well. And it's moving it 11 places to the left. This is the shift operator, and I show that in that video as well. And if you look at the reference manual, you'll notice that that's the 11th position. So it's taking a 1 and it's moving a 1 to the 11th position. And it's a 1. It's just like the number looks just like this. I'm going to use a comment for this. This is a 32-bit number, so this is the number. This is essentially what the register looks like, because you can see it has 32 places from 0 to 31, which is 32 places. And what this is showing you here, taking a number 1 and shifting it 11 spaces, is doing this. Putting a 1 in this location. That's all it's doing. And it is as simple as that. So this value here is the same as this value right here, which is the same as this value here, which is using the bitwise shift operator. And we're not going to be getting into complexities like this because there really isn't any need to do this unless we start to use functions and I show you in more advanced tutorials like I did in the previous series on how to set certain data pins of the LCD or something like that. So, but we won't be doing that for a while in this series. So I'm going to keep it as simple as possible. We don't have to worry about this stuff. All we really need to know is what bit we're affecting, and it's the timer 1 enable bit. That's it. So let's go ahead and enable the counter portion of this timer. We have to go back to the timer 1 section of this document, which is around 220, I think, or actually it was 267. Okay, so in the CR1 register for the timer 1, you'll see that there is a CEN, which is a counter enable. So we want to have the counter to be enabled. The counter is going to count up as fast as the system clock counts up, unless we divide it by some number. So let's see, where is that CEN? Should be at the end somewhere, I guess. Yeah, this is the counter enable. So to enable the counter, we want to write a 1 in that bit. So which bit is that? That is the bit 0, and it's called the CEN. So let's go ahead and do that. So we're using the timer 1, and we're using the CR1, the control register 1, and we're using the OR bitwise operation because we want to set the bit. We want to make the bit 1. So in here, we just use TIM, timer, because timer 1, timer 2, timer 3, they all have the same specifications or registers. So we're using TIM CR1. I'm going to use my control space to look at what we have here. So we have the CEN, counter enable. Let's go ahead and accept that. So now we've enabled the counter. Now we want to pre-scale the counter by 48,000. So we're going to use the, well, let's take a look at the reference manual and see what we can find here. We're looking for the PSC register. Okay, here's the timer 1 PSC. And this is a prescaler. It just divides the system clock, or the clock that the counter uses. And you can see that there's a 16-bit number here. A 16-bit number can go from 0 to 65,565. So that's why we can't just specify 48 million in this register, because we have to work within its bounds. So 48,000 is less than 65,535. So we can go ahead and use that number. So we're dividing the 48 million clock cycles, which is what the timer 1 is using, and we're dividing it down to 1,000 pulses per second. So let's go ahead and do that. So the timer 1 using the prescaler register, and we're going to just make it equals, because this is not a bitwise operation. We're just going to put a number in here, and this is going to be 48,000. Now we need to create the ARR number, which is the top trigger value that causes the counter to reset back down to 0. So the ARR value is the next one, which is the auto reload register. What this does is the counter will count up the 1,000 times per second, and we can put a value here. We could say 2,000 if we wanted to, like the ARR value would be 2,000. So that means that if the timer is now running at 1,000 times per second, it will reset every 2 seconds. But we want it to reset every 1 second, so we're going to put a value of 1,000 here. You can see that this is a 16-bit number as well, so it has a top value of, you guessed it, 65,535. So let's go ahead and put that in as 1,000. ARR, which is the auto reload register, and we're going to make that equal to 1,000. So now the ARR value is going to top out at 1,000 and cause the counter to reset back to 0 and then go back up to 1,000 again. So what we need to do now is use our new variable and make this variable equal the counter. And we're putting this inside of the while loop because we want this to continually run. We're going to get the value of the counter from the counter register. So let's take a look at that. The counter register is just above the prescaler register, and you can see that it can have a maximum value of 65,535. This register is automatically populated with a number of the counter value. So let's go ahead and access this register and take the number out of this register and put it into the variable that we created. So test count is going to be equal to the timer 1 count register. So all we're doing is we're accessing the count register, the counter value from timer 1, and we're putting it into the test count. We're assigning it to the test count variable. So now that we have a variable here, we can monitor this variable in the STM Studio. So I'm going to go ahead and plug in the programmer and program the microcontroller. And let's go ahead and press the play button and see if we have any errors. We have 0 errors and 0 warnings. And because this is a new project, it's going to give me the launch configuration properties. And I can check to see if the debugger has the correct information in here. I usually have this at none, so I'm going to click that, and everything else looks good. I don't need to scan this for the serial number, because if I change this ST link, then it'll give me an error and I have to rescan it. So I'm not going to do that. I'm going to go ahead and press OK, and hopefully everything goes well. Okay, we didn't have any errors after the download verified successfully. Because in the last videos that I wasn't able to get this to work, I wasn't using the VDDA and the VSSA. Let's go ahead and take a look at those, the power domain, and show you why that didn't work. So this is the data sheet for the microcontroller that I'm using. Let me make it smaller. We're going to go to the power supply scheme, or... Okay, yeah, it actually shows here that the VDDA and the VDDA and the VSSA, which is the same, it's just positive and negative. The PLL uses that portion of the power, the VDDA and the VSSA, and I didn't have those two connected, so I would immediately get an error here, and I would have to erase the microcontroller to be able to reprogram the microcontroller. But I have that connected, as you saw in the beginning of this video. So let's take a look and see the variable in action using the STM Studio. Okay, so the STM Studio, I'm going to have to import the ELF file for that project. I can go over here and get the ELF file. If I go to debug, you can see that there's an ELF file here. If I press the right button and I go to properties, I can copy this to the clipboard. Or I can just go there, because it's pretty easy. It's under the users, my name, and then STM32 CubeIDE workspace 18.0, and then the project name under debug, and then the ELF is there. So I'm going to copy this, and in the STM Studio, I'm going to right click here and I'm going to import, and this is the executable file that I'm needing here. So I'm going to just go ahead and press the ellipsis and paste it here. I'm using the Control V because it didn't give me the option when I right clicked it, and say select executable file, and it usually says this. I'm not sure why it says this, but the gdb command print x ampersand apb prsc table 0 failed, but that doesn't matter because all we're really care about is the test count. So I'm going to import that, close, and now I need to send this to the var viewer, which is over here. So I'm going to send to var viewer, and when I press the play button, since the microcontroller is already connected, it should show me the value. So you can see the count value is happening once every second. 1 1000, 2 1000, 3 1000, 4 1000, 5 1000, 6 1000, 1 Mississippi, 2 Mississippi, 3 Mississippi. So it looks like it is running at the correct speed at 48 megahertz because we divided it down 48,000 times, and then we're counting every 1000 ARR value, and we're looking at the counter that is counting up from 0 to 1000. Let's take a look at that again and make sure that it's counting up to 1000. So you can see the 1000 here, that's counting up to 1000, and it's going back down to 0. So it has that sawtooth look to it. Now what if we wanted to do this manually at the register level rather than using the IOC file? I'm going to go ahead and show that to you now. So I'm going to erase this system clock completely. This is the generated code, and I'm going to erase all of the comments since I don't need any of this stuff. I do want to keep the air handler just in case I use it sometime in the future. I always like to have it. I could use maybe the LED with this. Let's say light up the LED if there's an error happening in the code. I'm not going to need this call either, and I'm not going to need this function prototype because I took out the actual function. So I can remove that. So you can see all we have is the include. Let me save this so we don't have all those lines there. So we have the include, the main.h. We have our variable that we created, the HAL init. I'm going to keep that in. Probably not going to be using any of this. We have the timer code that we just put in, and we have the counter that is passed into the test count variable, and we have our air handler. So that's all we have in here. So now we have to create our own clock, and this is how you do it. We have to first make sure that we're using the HSI as our main clock, the high-speed internal clock. That is actually already set as default. So we don't actually need to put those lines of code in, but I'm going to do it anyway just as a confirmation that we're using it. So the clock and control register contains all of the clock source registers. So let's go to the reference and let's go to the RCC portion of this manual. Okay, so the reset and clock and control register. Let me go back up. So here's the reset clock and control section of the reference manual. It's on page 87. And here's the clocks portion of it. And it talks about the HSE, which is the high-speed external, and the HSI, which is the high-speed internal, and the PLL, which is the phase lock loop. And that is a far more advanced topic, and I have no idea how that works, and I'm not even going to get into that. But it is a way to multiply the HSI clock and the HSE clock, and probably the LSE and LSI, but I'm probably never going to work with these two clocks unless I absolutely have to for some reason. So the PLL, so we need to make sure that the HSI is selected as the main clock, and to find that out, we're going to go to the registers, find out how to do that. So the clock control register is the CR register, and you'll see that there is an HSI on, and we want to make sure that that is a 1. Let's go confirm that. Yeah, the HSI oscillator is on. So we want to make sure that is a 1 at that position. You can see that it is already on by default because this is an 83. The 3 value is actually a 1, 1. So this HSI on is already a 1 at reset. So let's go ahead and do that in the code and change this bit to a 1. Set this bit. How do we do that? We use the OR bitwise operation. All right, so we're going to go RCC, the control register, and we're going to use the OR bitwise operation, RCC, CR, and put the C in here. And the bit that we want to select is the HSI on. And now we want to make sure that the HSI is ready. So once we've turned it on, we want to wait until the HSI actually is on. We're going to use a while statement, and we're going to use the HSI ready flag. So this is the HSI RDY flag. Let's see how that works. So if it's a 0, then it is not ready. So we want to wait while it's not ready. So if it's equal to 0, then it is not ready. So let's go ahead and do that. I'm going to put another set of parentheses in here. RCC, CR, I'm doing this wrong here, CR, and the RCC, CR, HSI ready. If this is equal to 0, keep waiting because it's not ready yet. Now we want to make sure that the HSI, the high-speed internal oscillator, is being used as our system clock oscillator. And you do this through the CFGR, the clock configuration register. And we're going to use the SW, the first 2 digits of this register. Let's go take a look at what this SW requires. So the SW, the HSI selected as system clock is 00. So we have to make sure we have a 00 there. That is our reset value. So we don't really have to do this because our reset value is already 0 is a 00 in binary. And then we're going to use the SWS to determine that it is in fact changed to the HSI, which will also be a 00. You can see that it says read only. It's not read and write. This is a status. It just tells you what value it is. So once we set it to 00, we're going to read this and then make sure it's read at a 00. So we're going to use another while statement to determine this. So let's go to the RCC, CFGR register, and we're going to use the AND NOT bitwise operators for both the SW bits. I'm going to use the control enter to see, or control space to see the list here. And we're looking for the SW. That's the SWS, and this is SW. So if I put SW here, it's already the 2-bit digits in this register. So we can just do this in one line, just like this, because this SW actually shows a 1, 1. And when we're doing an AND and NOT, it is nodding the 1, 1, and it's creating a 0 for those 2 positions. So this is all we need to do, is do this in one line. So the SWS needs to be 0, 0. So let's go ahead and write the while loop to wait until that is a 0, 0. We're using the AND to do an AND bitwise operation here in the condition, the SWS, and this is going to be a not equal to, well, it's not equal to the HSI value, which is 0, 0. We're going to use the built-in definitions for this, and there should be one labeled HSI. So while it is not equal to the HSI, wait until it is equal to HSI, and then we can move on. Now, to use the PLL, the phase lock loop functionality with the internal oscillator, we need to first disable the PLL so we can make changes to it. And this is actually spelled out for you in the reference manual. Let's go to the PLL section. Okay, so in the PLL section, in the clocks section, there'll be a section devoted to the PLL. There's the HSI clock, and then there's a PLL clock. And right here it says disable the PLL by setting PLL on to 0, and I'll show you where that register is. Wait until the PLL ready is cleared, meaning that it's unlocked. At that point, the PLL is fully stopped. It's not working anymore, so we can make changes. We can now change the parameters. We can set the multiplication to 12, the PLL multiplier, and then we can start the PLL on again and lock the PLL. And the PLL ready determines whether it's locked or unlocked. which I'll show you in a moment. This is in the control register. So we're going to go to the RCC CR again, the control register, this one right here. And you'll see that there's a PLL on, which we have to set and reset. We're going to reset it first to turn it off. And we're also going to wait until it is ready. So you can see where it says locked and unlocked. So first we're going to turn the PLL off. We're going to make sure that the PLL is unlocked using the PLL ready flag. We're going to make the changes like multiply the PLL multiplier to 12. Then we're going to turn the PLL back on and then wait until it's locked. So we can't make any more changes. So let's go ahead and do that. So first thing we need to do is turn the PLL off. And that's in the RCC control register. And we're going to use the AND not bitwise operation to set PLL to 0 or off. We want this to be a 0, so we're doing the AND not bitwise operation. Now we're going to wait for the PLL ready to show us that it is unlocked. While it is, let's see, what number does it have to be? While it is not equal to 0, we stay in the loop because we want it to be 0. So let's go ahead and put in not equal to 0. I put these in here because if I wanted some code to be in here, I can put it in here. These are demarcations for code within these brackets. Just like the brackets with the int main, open and close, you have a bunch of code within it. Okay, let's see. Now we can create the PLL multiplier to 12. So let's go ahead and do that. And I think that's in the same register. Let's take a look. No, it's in another register. So let's take a look. CFGR. Okay, here's the PLL multiplier. So what does this need to be? The multiplier number 12. So what we need to do is we need to set these bits as 1, 0, 1, 0 in the multiplier section. So this should be 1, 0, 1, and 0. But there's an easy way to do this. Because first what we could do, because we don't know what's in these spots right now. We do know actually because it's a 0, 0, 0. This is the reset value, so they are all zeros. But what if we're in the middle of a larger program and we don't know how we set it before and we want to, reset it to a different number? This could be 1, 1, 1, 1 for all we know. So what we want to do is first turn those into zeros using the clock multiplier by 2. So we can reset those, all 4 of them, by using the AND NOT operation, and then we can use the OR operation with the clock multiplier for 12. So let's go ahead and do that. It's the CFGR, and we're going to use the AND NOT operation because we want all zeros in those 4 positions. So the PLL MUL, the multiplier, right here is 0, 0, 0, 0. So you can see that's going to show up as 1, 1, 1, 1, which is F. F is the same thing in hex as 1, 1, 1, 1 in binary. So what that's doing, this is just a mask. And what that's going to do is it's going to turn all those into zeros. 0, 0, 0, 0. RCC. Now we're going to use the PLL multiplier 12 and using the bitwise OR operation. CFGR and using the OR bitwise operation. So now we've assigned the PLL multiplier 12 inside of the CFGR register as 1010. So now we can go ahead and turn the PLL back on and lock it. I'm just going to go ahead and copy and paste that set of code here. And I'm going to use the OR bitwise operation to put a 1 there. Let's just make sure that that's correct. I have to go back to the CR. Here we go. Yes, so we're turning it back on and we're going to wait until it's locked. So we're turning it back on using the OR bitwise operation, and then we're going to wait while it's 0 because we want it to be a 1. So right here it's a 1 when it's locked. So we're going to keep waiting while it's a 0, and when it's a 1 it'll get out of this loop and go to the next thing. Now we want to use the PLL clock as our main clock now that we're using the PLL. So let's change it from the HSI to the PLL. We're not going to be turning off the HSI. We're just going to be assigning the main clock source as the PLL, but we're still using the HSI, so that has to remain on. So I'm going to go ahead and just copy and paste this part of the code, and we want to set it to the PLL. It's already 00, so we're pretty confident that we can just do this, SW and _PLL clock. So now we're assigning the PLL clock as our oscillator. Let's go ahead and just do a confirmation of this. That's in the CFGR register. That should be down here, I think. Yeah. All right. So the SW is the system clock switch, and PLL is 10, and that's what we want to select. So we're going to go ahead and do an OR bitwise operation and set it to the PLL. And then we want to make sure that it's, as long as it's stay in this loop while it's not the PLL. So when we're making the switch to PLL, we have to give the system some time to actually do the switch. And the status register, switch status, is giving us a status that it's switched to the right clock, and we're waiting until it's the PLL. So if it's not the PLL, stay in this loop. When it is the PLL, escape out of this loop and go on to the next thing. And that's it. That's all we have to do. So in review, we are turning on the HSI, the high-speed internal clock. We are using that as the clock source, which is really just making this 0, 0. We probably don't even need to do this, but I'm doing it anyway. It doesn't really matter. We are turning off the PLL so we can change the multiplication, and we're also unlocking it, waiting until it's unlocked. Then we're turning it back on. We are locking it back, so we can't make any more changes to the PLL. And then we're switching the main clock source, the system clock, to the PLL clock. So let's go ahead and try it out and see if it works. We should get the same values and timing for the timer 1 count as we did before when we used the IOC, the auto-generated code. So this is the register level code, which is just a few lines. It's not that hard. Just setting and resetting some bits. So let's go ahead and press the run. My microcontroller was still plugged in. We have 0 errors, and now it's connecting and transferring the program. The download verified successfully. Now it's shutting down. And now when it says shutting down, by the way, it's shutting down its connection to the microcontroller, but the microcontroller is still running because it's plugged in and it has power, but it doesn't have communication between the STM32 CubeIDE. And that makes it easy for us to use the STM Studio, because when we go to the STM Studio, we're not going to be blocked by any communication that's happening currently. We can just go ahead and press the play and it'll start doing it. But first we have to import that information. So let's go ahead and import. We're going to use that same executable file, but I'm going to go ahead and manually look for it. So I'm going to go to my PC, I'm going to go to my C drive, I'm going to my users, phood, going to STM32 CubeIDE, my workspace 1.8.0, and this is the one, this is my new project. And then we're going to go to the debug because that's where the ELF file is. So we're going to double click on the ELF file. We're getting that same error, but don't worry about that error. Give it to us twice for some reason, not sure why. I'm selecting the test count. That's our variable that we created. We're going to import that variable, click on close, and we're going to send this to the var viewer1 and play it. See if we get the same output. Yes, it looks like it's doing this every second. So we were able to change the clock speed using the auto-generated code with the IOC file, and we were also able to do it using the register level bit changes to registers. I hope this helps. I am doing this main change to work with the USART. I made this video only to show changing the clock speed because this can be used in any project. So if you need a faster clock speed for whatever project you're doing, use this video to do this. Most of the videos that I'm going to be putting out in this series is going to be more cookbook style. So you can just go to any video that you need to make changes. So like a video on setting up the USART, you can go to that video and set up the USART with whatever parameters you need, but using the guidance in the video. That video should show you everything you need to know to get that set up properly. Most of the videos in this series with the cookbook style of programming is not exhaustive, meaning that I'm not using every parameter and every variation of these peripherals and features of the microcontroller. There are literally millions of variations you can apply, and there's no way I would be able to show all of that. So I will entertain any user requests if you need to learn about a particular feature of a peripheral, if you want to learn about a particular feature and configuring that feature or peripheral. So let me know in the comments if you need to know how to configure a certain peripheral in a way that I'm not showing you, and maybe I can show that to you. Remember, if you're making these projects and you're putting them together yourself and you're making videos on YouTube, make sure to put the hashtag newbiehackarm as a tag for those videos so I can take a look at those videos and maybe make some videos reviewing those videos. And again, if you would like some help on your project or you want to show off your project, you can send it to me. I will provide my address after you send me an email talking about your project to customer service@buildyourcnc.com. That concludes this video. Thank you for watching.